Alright, so instead of previewing Chapter 7 like I said I was going to for this video, what I am instead going to do is I'm going to review all the stuff that we've done since 4.2 in our class. Essentially, a quick recap of confidence intervals and hypothesis testing and all of the different settings that we've seen them in. So what I did is I organized this by the section in our book, but really maybe these topics are more instructive. All the different topics that we've seen here. And what I want to comment color-wise, the red one is when we're dealing with proportions. The black ones are when we're dealing with means. And what I figured I'd do is just kind of take you through this chart, and maybe this works as a huge review of everything that we've done. So where this all began was back in 4.2 when we were first introduced to what were called confidence intervals. And the idea with a confidence interval is that you would have to be given X bar, the sample average, and then sigma, the population standard deviation, n, the number of observations in our sample, and our confidence level. And with that stuff, you could use the z interval function on your calculator. So you hit the stat button, then go over to tests. I think it's the first, no, it's not. It's like the 8th one listed. You look for z interval, and it'll ask you for exactly this stuff. It'll say what's x bar, what's sigma, and what's n. And it asks for sigma as opposed to like s because we're in a z interval. And the difference between a z interval and what we'll later see called a t interval is use a z distribution when you have means and your population standard deviation, sigma, is known. So if you don't have sigma and you instead have s, like we will later on, well then it follows a t distribution, so you use a t interval instead of a z interval. But back at this point, we either had sigma, the population standard deviation, or we did this little assumption where really it was the sample standard deviation that was given, but let's just pretend that's the population standard deviation so that we can use this z interval, because this is the first time we had seen any of this stuff. And at this point, we justified why the shape was approximately normal. And there are two different ways we could get that normality, either because n, our sample size, was greater than or equal to 30. 30 is just kind of an arbitrarily large cutoff that your book uses. Or because the parent distribution was assumed to be approximately normal. So either one of these two things happened. That told us the shape was approximately normal. It told us that we could use this z distribution because we had sigma and not s. And since it's a z distribution looking for a confidence interval, we used a z interval. This information was given, which was exactly what went into this calculator function. And then when you were drawing the picture, I guess I had you state shape, center, and the spread. The center was x bar, your sample average. And the spread was sigma divided by the square root of n. This is your standard error down here. And for the sake of drawing the picture, you throw x bar in the middle, and then the 2 points given out of your z interval function on your calculator describe your confidence interval. And that's how we first learned about confidence intervals. We then went into 4.3 where we dealt with hypothesis testing. Very different than confidence intervals. 4.2 and 4.3 were similar in that in both sections we had sigma, the population standard deviation. Or if we didn't, we assumed that the sample standard deviation was just the population standard deviation. Because we need that population standard deviation to get a z distribution, which is why we're using z interval and z test here. What happened is every time you're doing a hypothesis testing question in 4.3, you had to be given mu naught, kind of our baseline population average that we compared it to, x bar, our sample average, sigma, the population standard deviation, and alpha, which is 1 minus your level of confidence. So if you're testing something with 90% confidence or certainty, then alpha is 10%. And we justified back here why the shape was approximately normal. Same reason as why it was approximately normal in 4.2. Either the parent distribution was assumed to be approximately normal, or n was sufficiently large, greater than or equal to 30 is what your book said. When you're drawing the picture, mu naught, which was given you in the problem, is always what you used as the center. And if you were stating the spread, the formula for standard error, just like it was down here, is sigma divided by the square root of n. When we're doing hypothesis testing, you're always going to state your null and alternative hypotheses. Your null hypothesis is always that mu equals mu naught. Mu naught's going to be a number because that's given to you in the problem. It's like mu equals something, I don't know, 50. And then your alternative hypothesis would also compare mu and mu naught, except instead of an equal sign in between, you either put does not equal, less than, or greater than based on what it says in the problem, based on what the claim is. If I claim that something is greater than something else, then you're looking for a greater than sign here. And again, sometimes we didn't have S, or sometimes we didn't have sigma, but we had never heard of a t distribution at this point, so we really needed sigma. So even if we just had S, we were like, all right, well, let's just pretend that's sigma and call that good. So that was 4.2 and 4.3, which kind of laid the groundwork for everything else that you see in black here. So I'll go through the black stuff quicker when I get to it. But before I did, we also laid the groundwork in chapter 4 for all the red stuff, because we learned about proportions. And the big difference between the black stuff and the red stuff is in the black stuff you had averages, like sample averages, population averages. In the red stuff, you didn't have averages because your data was not numeric. It wasn't quantitative data. It was qualitative data. Instead of being numeric data, it was categorical data, specifically binary categorical data. So over here, you got a bunch of numbers for your data. Over here, you just have a yes or no is the way to think about it. So you're always given n, the number of observations in your sample, and then x, the amount out of that n that had the given characteristic. So if I'm talking about having blue eyes, 100 people, 80 of them have blue eyes, then n would be 100, x would be 80. P naught is kind of like mu naught is over here. It's the population proportion that's kind of the baseline that we're going to be comparing against. We're going to kind of take our sample proportion, which you get out of x and n. Our sample proportion is this p hat. It's always x divided by n. You can take that sample proportion and you can compare it against this kind of baseline population proportion p naught. Alpha also has to be given, same alpha as we have over here. The shape was approximately normal, and I had you justify why. The justification was different when we have proportions as opposed to means. Now it's p naught times 1 minus p naught that has to be greater than or equal to 10, as opposed to n being greater than or equal to 30, or having the parent distribution be approximately normal. When you're drawing your picture, you always put p naught in the center. Your spread is given by this nasty formula, which I had you memorize at one point. Your null hypothesis is always that p equals p naught. P will just be the symbol p. P naught will be a number given to you in the problem. You can do hypothesis testing, specifically a one prop z-test, when we first learned about proportions. You also could have built confidence intervals when you use a one prop z interval. So down here I talk about confidence intervals, although what you'll see is it's almost identical to what's up here. You also need to be given x and n so that you can figure out your sample proportion p hat. So here's x and n. There's no notion of p naught because you're not comparing, you're not doing a test against something else, nor is there an alpha, but you are given a confidence level. And yeah, you could argue that the confidence level and alpha are kind of similar, but I'm going to keep them different because I think that'll be less confusing for students. So you get x, n in your confidence level, which are the three things that go directly into your one prop z interval, and those spit out your lower and your upper bounds for your confidence interval. You draw your picture with p hat in the middle, and those lower and upper bounds, and you're good to go. The spread is the same spread. Well, it's almost the same spread as we have here. It couldn't be the exact same because there is no p naught down here with confidence intervals. Next best thing is p hat. So it's the same formula with p hats in place of the p naughts. And again, I noted here that p hat is just x over n. X and n are given to you in the problem. So 4.2, 4.3, and 4.5 are really the basis for everything going forward. So I went through those a little bit more slowly, I guess. I don't know how long this video has been going on. The way to think about it is if you can understand the three of these, all of these kind of follow naturally. 5.1, 5.2, and 5.3 are a lot like 4.2 and 4.3. And then 6.1 and 6.2 are a lot like 4.5. So let's get to it. In 5.1, we made the big realization that what we had been doing in 4.2 and 3 was a little bit misleading. Really, we could only do 4.2 and 4.3 if sigma was given to you. And often in those problems, sigma was not given to you, even though it says given here. What was actually given was s, but we assumed that s was the same as sigma, so it was as though sigma were given to us. Well, over here in 5.1, and you'll see also in 5.2, but let's stick with 5.1 for now. Sigma's not given to you. S instead is given to you. So what's given to you here is almost the same as what's given to you here, except I lied. You also need to be given n over here. I left that out. What's given to you here is the exact same as what's given to you here, except that instead of sigma, you have an s. And what that tells you is that instead of following a z distribution, this follows a t distribution, which is why we're using t-interval and t-test instead of z-interval and z-test. T-test is when you're doing hypothesis testing. The shape, the reason it's approximately normal, same as what we had over here. The center is still mu naught, same as it was over here. The spread is essentially the same, except instead of taking sigma dividing by the square root of n to get the standard error, well, there is no sigma over here. There's an S, so it's S over root n. You have S instead of sigma, which is why it's a t-test instead of a z-test. So your spread is going to be S over root n. Null hypothesis, identical to what it was over here. It's that mu equals mu naught. Mu naught is still a number given to you in the problem. Mu is just the symbol mu. When you are in 5.1, not only can you do hypothesis testing, but you can also do confidence intervals. The idea with confidence intervals here is they're almost the same as confidence intervals over here in 4.2. The difference is instead of sigma, we have an S. So your spread, instead of being sigma over root n, was S over root n. And instead of using z interval, I'm going to use t interval. Otherwise, what you see here is the same as what you see here. You still take x bar and put it in the middle, and you still get your upper and lower bounds for your confidence intervals straight out of the calculator function, t interval in this case. 5.2 was the first time that we saw two sets of sample data. We see that in both 5.2 and 5.3. But they're very different because in 5.2 we have what are called matched pairs. The way to think about matched pairs is if you have a single observation that you're tracking two variables for, as opposed to two different observations. So an example we used in class is textbook prices. If we have a given textbook and we figure out its price online and at the bookstore for one textbook, every textbook in our sample, maybe you have 10 of them, for each one you have the bookstore price and the online price, then you have matched pairs. Because each one of those observations, the 10 textbooks, has an online price and a bookstore price. Over here in 5.3, we don't have matched pairs because instead of having 10 textbooks with an online price and a bookstore price, you had 10 textbooks that had an online price and then 10 different textbooks that had a bookstore price. So you kind of had 20 observations in this example as opposed to the 10 over here. So if you have matched pairs like we were talking about, then essentially what you do is even though you have two samples, you treat it as though you only have one. How do you do that? You subtract the two of them. It makes sense. You can do the subtraction. If the pairs match up, it makes sense to subtract the two columns. So you're given two columns, and you subtract those two columns to form a third column. And on that third column, you essentially treat it like you're in 5.1. You do either a t-test or a t-interval. But instead of having mu naught, x bar, s, and n given to you, instead of having x bar, you have x bar of the differences, because you have this difference column that you created. Instead of having s, you have s of that difference column. N is still n, alpha is still alpha. Note that I didn't write mu naught over here for 5.2. That's because mu naught isn't explicitly given to you. We always assume mu naught equals 0. So that's here in the notes that mu naught equals 0. That happens in both 5.2 and 5.3. Your spread is mu naught, just like it was over here, and mu naught equals 0. So your center, sorry, did I say your spread? Your center is mu naught in 5.2, just like it was in 5.1. But mu naught equals 0, so the middle of your picture will have a 0 in it, similar on 5.3. The spread formula ends up being the same in 5.2 and 5.1, although I think by the time we got to 5.2, I stopped asking you about shape, center, and spread, at least this term I did. But it's the same formula, it's just now instead of S, it's the S of the differences column. But otherwise, this looks the same. Your null hypothesis is mu of the differences equals mu naught, just like it is over here. But mu naught is always the number 0, so I went ahead and wrote a 0 right here for you. You can also do confidence intervals when you have matched pairs. Same thing, you figure out a third set of data by looking at the differences. And on those differences, you can create a confidence interval. So it's x bar of the differences, the standard deviation of the differences, and in your confidence level that is given to you. The reason it's approximately normal, same reason it's been approximately normal. The center is the x bar, kind of like it was over here, although technically it's the x bar of the differences. And the spread is s divided by the square root of n, although technically that s is the s of the differences, which is why I put the little d in the subscript in this formula. Your picture, you're going to put your center as x bar of the differences, and the upper and lower bound, like has been happening on all these confidence intervals, comes straight out of your calculator function. 5.3 is when we really dealt with two samples that we couldn't just change into one sample like we did in 5.2 because we didn't have matched pairs. So this is where you had to involve some new calculator functions, a two-sample t-test or a two-sample t-interval, depending on whether you're doing hypothesis testing or confidence intervals. Either way, you're given the x bar, the s, and the n for your first group, and the x bar, the s, and the n for your second group, whether you're up here or down here. If you're doing hypothesis testing, You also are worried about mu naught, although much like in 5.2, we can assume mu naught always equals 0. So our center will be, in our picture, we'll have a 0. That's what mu naught is. And the spread, there's an ugly formula for the spread. I never even showed you it. You could Google it if you really wanted. It's a mess. I'm never going to ask you for what it is. It does exist. Similarly, the justification for why the shape's approximately normal, it's not quite as ugly, but I just said ugly formula because I never told you what it was. And my note here is the same as the note here, that mu naught equals 0. You're using a 2-sample t-test up here. You can also do a 2-sample t-interval. Same idea, the shape, there's an ugly formula. The spread, there's an ugly formula. The center, though, be careful. The center's not mu naught, which is 0. It's instead the difference in the two x bars. So x bar of the first group minus x bar of the second group. So when you're making a confidence interval, your center is not equal to 0. It's equal to the difference in the x bars, which sort of makes sense because our center over here has been the x bars, but now I have two different x bars. And that's where we finished up dealing with averages as opposed to proportions. We then jumped into 6.1. I really have nothing to add in 6.1. I think if you look at the 6.1 column, at least I hope if you look at the 6.1, it's the exact same up until you get to this notes as the 4.5 column. Really, 6.1 was just doing 4.5 again, reminding you of all that stuff you did in 4.5. It's identical, except that we added this fact that if you ever have a given, so you create a confidence interval, and maybe the margin of error isn't to your liking. So maybe you're asked a question like, well, how big would my sample size have to be if I wanted the margin of error to be some number? Well, we came up with this new formula for it. And I told you didn't have to memorize this formula. I just wanted you to be able to use it. So here it is. It's the formula that we introduced when we got to 6.1. But really, there's no reason we couldn't have done it in 4.5. It's just at that point, we were kind of learning the ropes for this stuff, kind of the basics. And that's pretty high-level stuff to use that formula. Finally, the most recent section that we did, 6.2, it's a lot like 6.1, except now instead of having one proportion, like we did in 4.5 and 6.1 to test, we have two different proportions. So instead of a 1 prop z test, it's a 2 prop z test. Worth pointing out that when you have proportions, you always follow a z distribution, so we don't have that issue of whether it's z or t. The way we decided whether it was z or t is whether you had sigma or s for your standard deviation. And there's neither of those when we're dealing with proportions. There's no notion of a standard deviation in those cases. They always follow a z distribution. So in 6.2, you always have to be given x and n like you were over here, except now there's two groups of them. There's x and n for the first group, and there's x and n for the second group. And then you are also given alpha that you're going to be testing at. Note that I didn't write p naught over here. Why? Because much like in 5.3, the thing that's like mu naught, p naught, is always equal to 0. So I put that in the notes. P naught is always equal to 0. So your center is always going to be equal to 0. And that's not explicitly given to you in the problem, so I didn't list it up here. There's an ugly formula for shape and spread, so you're not worrying about those. Your null hypothesis, instead of comparing p and p naught, it compares the two different p's, the p of the first group and the p of the second group. When you have two different proportions like this, not only can you do hypothesis testing, you can also do confidence intervals. With confidence intervals, you're given almost the exact same thing as you're given up here in 6.2. The only difference is instead of alpha, I wrote confidence level. And yeah, those two are similar. But your calculator specifically asks for the confidence level down here in 6.2, whereas alpha is what's used. Sorry, I shouldn't have said 6.2. It asks for the confidence level when you're dealing with confidence intervals. And you need to know alpha when you're doing hypothesis testing. So even though those two things are very related, I wrote them a little bit differently here. When you're drawing the picture down here, your center is the difference in the two p hats. Very similar to over here, where it's the difference in the two x bars. The difference in the two sample proportions, which is what p hat is. And that's x1 divided by n1 is p hat 1, and x2 divided by n2 is p hat 2. So you have this center. The upper and lower bound come straight out of your calculator, and that's everything you need to know for 6.2. Big picture stuff that I didn't write on here, but maybe that's worth talking about, is you always reject your null hypothesis if your p-value is less than alpha. If there's one sentence to have memorized for this class, it's that one. Say that over and over again. Reject your null hypothesis if your p-value is less than alpha. Conversely, You fail to reject your null hypothesis if your p-value is greater than alpha, or greater than or equal to if you really want. So that's how you make your conclusions when you're doing hypothesis testing. One other comment I wanted to make about hypothesis testing. You might be wrong. You'll never know that you're wrong, but there's these things called decision errors, and they're kind of a hypothetical construct. And the idea there is there's a type 1 and a type 2 error. What you need to know about those is a type 1 error happens when you incorrectly reject the null hypothesis. So there's only two possible conclusions. Either you reject the null hypothesis or you fail to reject the null hypothesis. If you reject the null hypothesis, you're concluding that your claim is true. If you fail to reject the null hypothesis, you're not really concluding anything. You're just saying there's not enough evidence to say that the claim is true. You're not saying that the claim is false, just that there's not enough evidence to say that it's true. Anyways, if you do that first conclusion where you reject the null hypothesis and therefore conclude that the claim is true, if you come to that conclusion, but you were wrong, you'll never know that you were wrong, but hypothetically speaking, if that conclusion were wrong, it's called a type 1 error. If you do your second conclusion, where you fail to reject the null hypothesis, but you were wrong, you fail to reject the null hypothesis, you don't say that the claim is true, but really the claim was true. That's what's called a type 2 error. So if you reject the null hypothesis, aka say the claim is true, but in reality the claim is not true, it's a type 1 error. And the other way around is a type 2 error. The probability of committing a type 1 error is alpha, and the probabilities of committing those two errors are what's called inversely proportional. So you get to choose how likely a type 1 error is, but if you make it super duper likely, then you're making a type 2 error super unlikely. And if you make a type 1 error super unlikely, then you're making a type 2 error super likely. And I think that is all the different things, or at least most of it, that we've talked about with confidence intervals and hypothesis testing. So hopefully this works as a good review. This definitely wouldn't be a good way to learn stuff because it's way too quick to learn stuff. But maybe if you're already somewhat familiar with all this, that was helpful to you. If not, sorry for wasting your time.